Hi everybody, welcome to Current Mesh Analysis. This is the first video in a two-part series, and this first one is going to address the understanding behind the current mesh analysis, and the second part of this series is going to be refining this technique down to get it as quick as possible for your exam time. Current mesh analysis can be broken down into three main steps. The first step is to define mesh currents. And I'll get into what those are in a second. The second step is to write KVL loop equations. And step 3 is to solve. Before we start any electric circuit analysis question, the first thing we need to do is set a reference node. A reference node is essentially ground in our circuit, and if it's not set for you, you can choose anywhere on the circuit to place the reference node. As a rule of thumb, in a circuit that looks similar to these, place it at the bottom here, as most textbook questions are set up for this to be the easiest way. Now that we've defined our reference node, I'm going to get into what meshes are. So in electric circuits, we define meshes as loops within a circuit. So we can see we have one loop here, another loop, and a third loop around these branches here. So essentially they kind of make a mesh that you see in fly screens. In the mesh current technique, what we do is define an unknown current in each of our meshes. So in this first mesh here, we define one as IX. In the second, we define another one as IY. And in the third, a third current as IZ. And by convention, we always draw these currents clockwise. That is our first step done. Our second step is to write our KVL loop equations. So as a recap, KVL, or Kirchhoff's voltage law, is that the sum of voltage rises equals the sum of voltage drops. How we go about developing these equations is to look at each individual mesh separately. So I'm going to look at mesh X first. Mesh X. To develop these mesh equations, we start at the reference node inside of our mesh. So that could be this corner down here or this corner down here, as these are both the same node. What we do is then trace the path the current would take. So we can see we've defined the current to be going clockwise around this loop, so we need to follow that path. As we work our way up here, we encounter a battery source. We can see that we are at the negative terminal of this battery source, which is the low potential side. We then move up to the higher potential side. So moving from low potential to high potential is a voltage rise, and that must go on the left-hand side of our KVL equation. So we have a voltage rise of V volts. We then continue tracing this current around up to our resistor. Resistors are defined as voltage drops. That is their definition and their purpose inside of a circuit. So a voltage drop is always current traveling from high potential to low potential. So we can draw on positive and negative terminals here to show that voltage drop. To find the voltage drop for this resistor, we use Ohm's law. V equals IR. Now we've defined what the current inside this loop is. It's IX. So the current flowing through this resistor is going to be IX. We then multiply IX by the resistance that the current is encountering, or R1, and that gives us the voltage drop over resistor 1. We then continue along the path through our loop down to R2. Now again, R2 is going to have a voltage drop, which will be a positive to a minus flow. One thing we have to be careful of here is that we have two currents clashing heads inside of this branch. If we look at R2, we can see we have IX traveling down towards the ground node in this direction, and IY traveling back up the branch in this direction. So our overall current traveling through this branch is going to be the difference of the two, or IR2 is equal to IX minus IY. So if we write the voltage drop over R2, it will look as follows. It will be the current flowing through R2, which is Ix minus Iy, times the resistance it's encountering, which is R2. And then if we continue following this path around back to the start, we find we don't encounter any other objects inside of our circuit. So that is our mesh KVL equation for mesh X. We must then repeat this process for the other two meshes. So let's do mesh Y. Mesh Y. If we then repeat this process where we start at the reference node and work up, we find ourselves traveling from the negative terminal of resistor 2 to the positive terminal of resistor 2, which is a voltage rise. So this must go on the left-hand side of our KVL equation. The current flowing through this branch we defined before as IR2 being the difference in Ix and Iy. So our voltage rise is going to be Ix minus Iy times R2. And if we follow the current further along this path, we reach R3, which is going to be a plus minus. So we have a voltage drop over R3, which is going to be Y times R3. And we continue our path down through R4, which is going to be a voltage drop of R4. And again, we have two currents clashing heads, so our current is going to be Iy minus Iz. And then we continue our path back around to our starting point. So that is our mesh Y KVL equation. Something I want to address is how do we know whether resistors have plus or minus terminals? And the answer to that is you need to identify what the current is going to be doing inside of the circuit. So if we trace around from our battery source here, we know the current's going to be pushed away from our positive terminal, up through resistor 1, and then it's going to want to come down to our reference node, which is our point of least potential. Some is then going to branch off into R3 and then want to come down here. And we know our current source is going to drive current around here. As resistors are always voltage drops, we need to define the positive terminal as where the current is entering. So as current is going to be passing down this terminal here, we obviously have a plus at the top here. It's going to be running through this way. We're going to have a plus at the top of R3, and it will come down this branch here to flow to the point of lowest potential. So we'll have a positive at the top of R4. Now let's do our third and final mesh KVL equation. Mesh Z. Now the interesting thing about mesh Z is that we have a current source inside this mesh. A current source defines the direction and magnitude of current within that loop. So it actually tells us directly what Iz is. We know Iz is equal to minus I. It's minus I as it's traveling in the opposite direction to what the current source is defining. Those are our three KVL mesh equations for our three meshes within our circuit. Our job now is to solve for Ix, Iy, and Iz. Now we have three unknowns in this case, but we also have three KVL equations, which means this is a solvable system. You can solve this system by substitution, elimination, or using matrices. My preferred method is to do substitution. The first step to identify here is that we already have Iz defined for us. Our third KVL equation gave us the value of Iz. So what that does is collapse our three unknown, three equation system into a two unknown and two equation system, which is awesome for using substitution. What we need to do now is substitute in Iz wherever we see it in our other two equations for its value negative I. So I'm going to rewrite mesh Y down here in its new form. In the process, I'm also going to expand out the brackets to make it easier to rearrange for Ix and Iy. So we have Ix R2 minus Iy R2 equals Iy R3 plus R4 Iy plus R4 times I. This is going to be our fourth equation. Grouping these equations in terms of Ix and Iy is a very handy step when doing substitution, so let's do that. Getting all of my Ix terms to the left-hand side and all of my Iy terms to the right-hand side with any other constants, we get the following. Ix R2 equals Iy out the front of R2 plus R3 plus R4 plus R4I. Rearranging for Iy, we have Ix R2 minus R4I divided by R2 plus R3 plus R4 equals Iy. Now that we have Iy, we can substitute this equation 5 here back into equation 1. So substitute 5 into 1. We can then rearrange for a value of Ix. So essentially that substitution there will give us a value for Ix. We then substitute the value of Ix into equation 5, and that will give us a value for Iy. Once we have Ix and Iy, we've actually solved our system. We already started with Iz, and now we have Ix and Iy. Once we have Ix and Iy and Iz, we know everything we need to about this system. We can solve for all of the currents through each resistor, as the current going through this resistor here will be Ix, as we can see in our diagram. The current going through R2 will be Ix minus Iy, as we defined before. The current going through R3 will be Iy. The current going through R4 will be Iy minus Iz. And this current coming through here will be I. We can then solve for the voltage drops over all of the resistors or any other questions that might be posed for us. So that is current mesh analysis. Hope you guys learned something. Please check out the next video where we refine this technique down into a simpler and faster method for you guys to take into exams.